assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So to write down the ground state electronic configuration for elements and ions, we need to follow the steps mentioned here. So first of all, we need to find out the preceding noble gas. Um, that means the noble gas that precedes the element or the ion we are going to write down the electronic configuration, and we have to put that noble gas in a square bracket, and followed by we have to identify the principal quantum number of that element or ion, and the principal quantum number is basically the the period number or the number of row in which the element reside in the periodic table. And then we have to uh, write down the s electrons like ns, and then if we have d electrons, we have to subtract 1 from the principal quantum number, and you have to write down n minus 1 d. And then if we have f orbital electrons, which happens only for row 6 and the later rows, in that case we will have to write down the f by subtracting 2 from the principal quantum number. So first we have to put the noble gas in square bracket, then we have to write ns, then n minus 1d, and then n minus 2f. And then we have to count the total valence electrons on that element, which is basically we can count it by just going through the specific row in which the element resides. So for example, if our element reside in row 3 and its position in the row is 5th, then the total valence electrons on that element is 5. And then we have to distribute the electrons accordingly, like they will first occupy the s orbitals, and then d orbitals, and then f orbitals, or something like that. And for ions, then we have to remove the electrons equal to the number of charge we have that on that ion. So for example, if an ion has -2 charge, for minus charges we will have to add electrons, and for plus charges we will have to remove electrons. So for example, if an ion has +2 charge, we'll have to remove 2 electrons from the total valence electrons, and while removing electrons, we will have to first remove electrons from the s orbital and then from d orbital. So that's the principle how we write down the ground state electronic configuration. Now let's just first do it for the zirconium. So first we have to find out the noble gas preceding zirconium, which is krypton. Then we have to um, find out in which period or in which row zirconium is. So zirconium is in 5th period, so we have to write 5s. And then uh, we have to write the d orbitals in n minus d form, that means 5 minus 1 4d. And in next step we have to, okay, I forgot to put the square bracket on krypton. And then so the zirconium has total 4 valence electrons, so we have to distribute the 4 electrons between these s and d orbitals. So first we have to put two electrons on s, since that's the maximum number of electrons an s orbital can afford, and then the rest of the 2 on d orbital. So this is the electronic configuration for zirconium. Then let's do it for zirconium 2 plus. So as we said that in case of ion, we just need to subtract the number of electrons equal to the number of charge, and since here we have 2 plus, that means we'll have to remove 2 electrons from the zirconium element electronic configuration. And since we have to remove the electrons from the s orbital first, so our zirconium 2 plus electronic configuration is as before. Krypton is the noble gas. Then we have to remove the s electrons. That's why we will not have any s electron here, so we'll have only 4d2. So that is our electronic configuration for zirconium 2 plus. Then let's find out the electronic configuration for cobalt. So for cobalt, the noble gas that precedes cobalt is argon. Then cobalt is in a fourth period or fourth row, so our s, we will have to write 4s and n minus 1d, that means 3d. Now cobalt has 9 valence electrons, or 9 more electrons than argon. That means we'll have to distribute these 9 electrons between these two orbitals. So s orbital can occupy 2, and the rest of the 7 electrons will go to the d orbital. So argon in third bracket or square bracket, and then 4s2 3d7. That is our electronic configuration for cobalt. Then in case of cobalt 2 plus, we just have to remove 2 electrons from the cobalt element, and we'll have to remove these 2 from the s orbital. So cobalt 2 plus has an electronic configuration of argon and then 3d7. Then let's find electronic configuration for this Tc. So the noble gas preceding Tc is again krypton, and so Tc is in the fifth period. So again we have to write 5s and n minus 1d, that means 4d. So Tc has in total 7 electrons, so 2 will go to s and 5 will go to d. Okay, and then we have to find out electronic configuration for Tc3 plus. That means that we will have to remove 3 electrons from here. So we'll have to remove these 2 and 1 from here. So our electronic configuration for Tc3 plus will be 4d4. Now let's find out the electronic configuration for osmium. So the noble gas that precedes osmium is xenon, and so osmium is an element from the sixth group. That means we'll have to write 6s, 6th row or 6th period, not 6th group, and then I will have to write n minus 1d, which is 5d. And as we said that for 6th row or later rows, we'll have to add the f orbitals as n minus 2f. That means 6 minus 2, we'll have to write 4f. Now osmium has total 22 more electrons than this xenon, and then we'll have to distribute these 22 electrons here. So first 2 electrons will go to 6s, then 14 of the electrons will occupy this f orbital, because we know that electrons will occupy 4f before 5d, because because for finding out where electron will go first, we have to um, just sum up the principal quantum number and the azimuthal quantum number. So in case of 4f, we have a total value of 4 plus. For f, the value is 3, so in total value is 7. And for, so this is for 4f. And for 5d, the value is 5 plus. For d, the value is 2, so 5 plus 2 is 7. But since the principal quantum number of 4f is smaller than the 5d, that's why electron will occupy 4f first. So we'll have to put 14 electrons in 4f, and then the rest of the electrons, which is we have 6 more electrons, so these 6 electrons will go in 5d. So that is the electronic configuration for osmium. And then for osmium 4 plus, we have to remove four electrons. And so again, we have to remove the s electrons first, and then we will have to remove 2 of these d electrons. So our electronic configuration for OS4 plus will be xenon, and then we don't have any s electron, so we have 5d4 and then 4f14.